Well, welcome back, and now we're going to talk about the first topic in this section is not really about climate change, although it's critical underpinning. We're going to talk about energy. We have energy everywhere around us. We use energy every day in our lifestyles. We get energy from the sun, we get energy from lights, we get energy from fuel sources. But we're going to talk about some of these concepts of energy and also about power. So what we're going to do is really think about some of these different sources of energy. And the main source of energy is the sun. So the sun's the dominant source of energy. Where actually the sun provides its energy through sunlight, through radiant energy. Sunlight we see every day. But that energy has then been harnessed, converted into fossil fuels by photosynthesis, and we harness that energy in lots of different things. In transport, aeroplanes using aviation fuel, we use it to harness the energy from wind turbines. There are lots and lots of different ways. We also have energy that's being captured and transported through power lines, energy from fossil fuels or energy from solar cells. We have to transport that. We have energy used in telecommunications, in our telephones, in our televisions, in a range of different sources. We use energy in our cars, and the energy in our cars is provided by petrol or gasoline. We have energy from electricity in our light bulbs, where energy is crucial. The rate that we use energy is called power consumption, and there are lots and lots of different ways. We use energy in running the internet, in telecommunications. We use energy in so many different ways. Computers, cars, transport, cooking food. A modern society consumes lots and lots of energy. So what we're going to talk about in this lecture is really the difference between energy and power, power being the rate of use of something. And the easiest way to think about these in terms of analogies, or if you like metaphors, discussion, is to think of energy in terms of the amount of money you've got. And the unit of the amount of money, most of us know, is the dollar. The unit of energy is the joule, named after a scientist. You don't actually have to know very much about the scientist, but the joule is the standard unit of energy, the dollar, standard unit of money. So when we talk about energy, we talk about that being measured in joules, and then we think about dollars. $100 is, a moderate amount of money, but 1 joule is the energy required for 1 heartbeat. The amount of energy stored in a mobile phone battery is about 10,000 joules. The amount of energy in this standard tank of petrol or gasoline in a car is 2.4 billion joules. So there's a lot of energy stored in fossil fuels. Now that energy and a tank of gasoline will drive a car, a long distance, maybe 1,000 kilometres if you're lucky, maybe only 500 kilometres. But when we talk about the rate of use of energy, it's the number of joules per second. And that unit is now called a watt, again named after a scientist, Charles Watt, who essentially developed this, if you like, unit of energy use. A watt is 1 joule per second. And typically, a person working will be consuming energy as an average worker at 500 watts. In other words, 500 joules per second. We think about cooking toast in the morning. It's a typically 2 kilowatt toaster. In other words, that's 2,000 joules per second. When we're heating up water in a kettle, it might be a 5 kilowatt or a 2 kilowatt electric kettle. But then there's a lot of people every morning who would be turning on their kettles or turning on their toasters to prepare breakfast or to cook dinner. And so a large power station produces 1 gigawatts. That's 1,000 million watts, or 1,000 million joules of energy used up every second from a power station. And most cities, 4 million people, would be using energy at the rate of 7 gigawatts, or 7,000 million joules per second. And in a day, there's 60 seconds in a minute, 60 minutes in an hour, times 24 hours in a day. It's 60 times 60 times 24 times 7,000 million joules in a day. A lot of energy use in a typical city. So then we think about a country, 23 million people. That's 45,000 million watts. That's essentially the energy consumption in Australia every second. Australia with a population of 23 million people. Energy use and how we provide that energy is key to this issue of climate change. And we can also think of another unit, kilowatt hour. That's a kilowatt of power combined over an hour. 24 kilowatts hours would be a kilowatt of power consumption over a whole day. And that corresponds to, as we said before, 3,600,000 joules, or that's the number of seconds in an hour, number of what is a kilowatt hour. So, Western civilization, or Australia's energy use, is critical. And what we've got to do is find, through a range of different energy sources, the power that is needed to provide that 24 billion gigawatts that we're using all the time. So, where does that energy come from? Well, that energy comes from either fossil fuel power stations or electricity generated from coal or oil, or renewable sources like hydroelectric power stations. And currently, Australia's power consumption is about 45 billion joules per second, or that 45 gigawatts of energy use. And if we look at what our, if you like, energy capacity is in terms of cars, trucks, aircraft, not the fixed energy consumption, but actually the mobile energy consumption from petrol, from diesel, from aeroplanes and trains, it's about 40 billion joules per second. Nearly as much as that fixed stationary energy use is actually in the petrol and diesel and planes and trains that are using up all that electricity. Energy use is critical to modern society. So there are some fundamental physical laws that determine how energy is gained or lost. And the most important thing is that first law of energy is that energy is conserved. Can't be created except from nuclear reactions, but in a typical system, energy is conserved. It can be converted from one stable energy source, what we might call the potential energy, into thermal energy or kinetic energy of motion. It's possible to convert energy from one source to another, but energy is in total conserved. It can't be created or destroyed. We have nuclear energy conserved in the composition of materials that can be converted into electrical energy or power through nuclear power stations. We have energy stored away in fossil fuels. The second law of thermodynamics, another fundamental law, says that it's not possible to completely efficiently convert heat, stored energy, into work, electricity. Can't be 100% efficient. So that means we lose some energy every time we take stored energy and convert it into electricity. We lose some energy into heat. We lose some energy through friction. Every system will lose energy. And more particularly, we also can't have heat or energy flow from a lower temperature object, a colder object, into a hotter object. Typically, heat energy will flow from more energetic, hotter systems into colder systems. But in fact, all objects, and we're going to hear more about this later, all objects radiate energy out to space. So radiation can in fact be a way that Objects at lower temperatures lose energy, as well as just standard conduction. And we're going to talk about that later on as well. So, not all energy, not all objects, their energy that they contain can actually be harnessed. Yes, we can use energy from mobile phones, but sometimes harnessing energy from different objects won't be very efficient. And so we look at a battery in a mobile phone. It contains 10,000 joules. And yes, we can use that. We can charge it up again by plugging it into the wall. We can use that energy for our telephone. There's actually more energy contained in the hot water in a bath. About 80 million joules of energy contained in a bathtub full of water that's about 60 degrees Celsius. There's 80,000 joules of energy, 80 million joules of energy that will be released when that bath cools down to just the ambient temperature of 20 degrees C. But we can't harness that energy in any efficient way. We can't efficiently and effectively harness that energy to charge up a battery. What we need to charge up a battery is a compact and efficient energy storage or energy transfer system, and we don't have that in terms of capturing the heat energy from a bath, or not at present. We don't have a system. Yes, you can't plug your phone into a bath and get the energy out. You can plug your phone into the wall, or you can find a bigger battery and plug your phone into a bigger battery. There are ways you can do that. So, let me try to summarize. Energy is this store of, if you like, fuel that underpins modern society. Power is the rate of consumption of energy. And we can think of energy like a store of money. It drives modern society. It's critically important to understand that, in fact, all the energy that's around on the Earth at present originally came from the sun. And each day the sun adds more energy to the system, and our system loses energy out to space. We're going to hear more about this balance of energy between the energy gains from the sun and the energy loss out to space. There are some systems where the energy's been stored, and one way is these fossil fuels that I've talked about already have stored energy. Photosynthesis takes energy from the sun and stores it away in carbohydrates, material in plants. That carbohydrate is really important for our food, but it is also critically important as a future energy source when it's buried underground and then dug up again, converting those carbohydrates into energy for driving power stations, for burning. And we burn those fossil fuels, and unfortunately the waste products from burning fossil fuels is carbon dioxide that goes into the atmosphere. The other big problem is, as I've talked about, we lose energy. We can't uniformly and efficiently convert 100% of stored energy into useful purposes for driving cars or generating electricity without energy losses on the way. So, in the next lecture, I'm going to cover a little bit more about this balance of energy and how this energy from the sun drives the climate system and the role of greenhouse gases in affecting the temperature of the planet and its climate.